The first one's deceivingly hard because it looks like just like what we've been doing, but it's written a little bit differently. It says, I know my first term is 5, I know a sub 2 is 7, but then it says a sub n plus 1 equals a sub n minus 1. So in just English, if this is the term I want, what is this one? John? It is 2 terms before. Because if I have a sub n plus 1, one term before would be a sub n. So 2 terms before would be a sub n minus 1. So let's look at 2 ways we could actually solve this. So if I have a sub 1 equals 5, I have a sub 2 equals 7. Just in plain English, this says the term I want equals 2 terms prior plus 5. So if the term I want is a sub 3, 2 terms prior would be 5, so just be 5 plus 5 is 10. How this would look algebraically with the n's is I would have to change this to a sub n plus 1 to match this form, to know what my n value is. That would mean this equals a sub 2 minus 1 plus 5, but a sub 2 minus 1 is a sub 1, so it would be just like we said, it'd be 5 plus 5 equaling 10. But if you can say that in just plain English, it makes your life a lot easier, because a sub 4 would be 2 terms prior, which would be 7, plus 5, which would be 12. So that's why I've been practicing with you guys just saying this in plain English, because we shouldn't get recursive problems wrong. Yeah. You sure? What was your question? Just
is it not arithmetic?
Is it not arithmetic? It would be arithmetic because you had 5 to each one. But it doesn't start off arithmetic, so as a whole it would not be arithmetic. So it's an arithmetic sequence minus our starting off points, so it wouldn't be arithmetic. We'd actually have 2, I don't want to get into it, we have alternating arithmetic sequences combined. But that's pretty advanced, and we're not going to deal with that. So if you wrote out the terms, it wouldn't be arithmetic. Okay, did you have a question too?
That's the same question.
Oh, okay. Just because it goes 5, 7, 10, 12, plus 2, not plus 2, automatically not arithmetic, but you do have alternating arithmetic. See, it's weird. We're not going to get into that, and I didn't feel like I should set up that. But all right, the next one says write a series in summation notation. Anytime you see minus, plus, minus, plus, minus, plus when we're dealing with arithmetic sequences, so this is just with arithmetic, we're going to go ahead and write this as, I see that we have a negative, and we're alternating positive. So that means I need to have negative n, or negative 1 to some power. And it's either going to be n plus 1, n, or n minus 1, or something with n. Does anyone know what I want that power to? Callie? N. Just to the nth power. Well, if Callie's right, that means if I plug a 1 in here, that makes this negative, so my first term better be negative. It is. So n works. So that's going to be the thing that alternates. As soon as I know what's alternating, I can think of this sequence as just being, I'm going to change it to 1 over 1, 1 over 2, 1 over 3, 1 over 4, because I got rid of the alternating, and this is in the denominator plus 1, in the denominator plus 1, in the denominator plus 1. So my sequence in explicit form is going to be 1 over just n. And if we went through the whole checklist, it would be 1n plus c, which would be our first term minus our difference, so it would be 1n plus 0. I don't feel like doing that, it would just be n. So in sigma notation, I'm going to start at 1, I equals 1. We're going to go all the way to infinity, and it's going to be negative 1 to the n all over n. Questions, comments, concerns on those? Yes?
Does it matter if you have the same variables, like you have I and n as well?
It does not. Most of the time we use I, K, J in for this, and we basically can use n's or whatever we want over here. Sometimes they match up, other times they don't. All right, because all this is my index. It says start your variable at 1 and end at infinity, and my variable just happens to be n. So in fact, 99% of the time, this won't even be the same variable. Sometimes they match up, but most of the time, this is I and this is n. It's just kind of tradition. All right? So that brings up a good point. This doesn't say that I equals 1. I mean, it just says your index is 1, your first term. It starts at 1, so that just means plug it in here. All right, it's a little nuanced, so it doesn't say n equals 1. It says your index is 1. So make your n 1. I think I made it muddier than clear. So no, in the end they don't have to match up, and most of the time they don't. Okay, what questions do we have from the homework? Brian? Number 11. What are we supposed to do? We're supposed to find the sum of each series. Well, that is... So we start at 7, right? And we end at 44. So let's just come up with this pattern. Our very first one is negative 1 to the 7th power, which is going to be a negative 1. Then it's going to go plus 1, because this would become 8, it'd be even, so this would cancel out. It becomes 0. Then it becomes odd, which makes it negative 1 again, and then even, which cancels it out again. So the only thing you have to do is this going to end on an even number, which cancels it out? Odd number, which is going to leave it as negative 1. So I look up here and it's 44, which is even. So that means I go dot, 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 dot. Too many dots. Dot, 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 dot. And we'd end on a positive 1, because that would be negative 1 to the 44th, which makes it positive, which means it just turns to 0. Does that make sense why it's 0?
Yeah.
Yeah. I didn't actually want you to plug in 7 through 44 in this problem and just write negative 1 plus 1, negative 1 plus, because that'd be a waste of time. So that's just going to equal 0. If it ended on an odd, if it was 43, it would have been negative 1, would have been the answer. So there's only two options, negative 1 or 0. You just got to figure out where it ends. All right, other questions? Yeah, Lee.
Number 39.
Number 39. Is that a tough one? Okay, so we have to rewrite this. At first my index started at 2, now it ends at 5, so I'm adjusting up 3. And if I'm adjusting up, so we're adjusting up 3, which I have to adjust the top and the bottom, so I have to have infinity plus 3. I'm pretty sure that's still infinity. I don't actually know the number for infinity, so we're going to leave that as infinity. But if I'm adjusting up 3, that means I need to replace my variable with what? If I'm adjusting up 3, is it going to be n minus 3 or n plus 3? Lena? Minus? Yep. You're right. It is minus. And the way I think of it is because I add 3, so I have to subtract 3 to keep it balanced. So we're going to replace every n with n minus 3. So we're going to have 5 times n minus 3, or n to the n minus 3. We leave the e to the negative 5 alone because there's no n in there. And on the bottom it's just going to be n, that's an m, n minus 3 factorial. The factorial was there, so let's leave it in black. And I'm just going to really quickly check to make sure it makes sense. Well, if I plug 2 in, this would be 2 factorial. If I plug 5 in, 5 minus 3 is still 2 factorial. If I plug 2 in here, I have 5 squared. If I plug 5 in for that n, I have 5 minus 3, so it's still 5 squared. Everything matches up. Okay? Other questions? Yeah, John. 35. You're too close to me. I couldn't see you. All right, same thing, except now we're adjusting down. We're adjusting down 3. I'm going down 3 units, which means I need to go down on the bottom, and on my top value, I also have to go down to 10. If I go up, I subtract. If I go down, I add. So rather than writing 2i, I'm going to write 2 times I plus 3 plus 1. I would distribute and simplify. All right, so it would actually be 2i plus 7. So I subtracted 3 from my starting and end terms, which means I have to add it back in here. Other questions? Yeah. 17. Write each series in a summation notation. So I'm going to jump right to, well, we're going to need a -1 to the end to account for that alternating, which really means that I just have the sequence 1, 3, 5, 7, 9. That's plus 2 across the board. So we're going to have a sub n equals my difference times n plus c, where c is my first term minus my difference, so it's -1. So we're going to end up with just the summation from I equaling 1 to 1, 2, 3, 4, 5. I have 5 terms. And we're just going to have that -1 to the n out front times 2n minus 1. It was quick, but does that make sense? Okay. Other questions? Okay, then let's get on to today's lesson. I'll leave that up for a couple more seconds. And today's lesson starts out with a story about a guy named Carl Gauss. This is the same Gauss that came up with that Gaussian elimination that we use. Gauss is one of the most famous mathematicians ever to have lived, and he actually butted heads with Isaac Newton over calculus. Isaac Newton is credited with our calculus, even though we use Gaussian terminology and how he did it. But anyway, Gauss, one of his famous stories was when he was a little kid. I guess he was a little bit of a troublemaker, and his teacher always wanted to get him out of his hair, and that happens with a lot of smart students. They seem to bug teachers because they ask questions and they want to know their answers to stuff. So he was bugging the teacher one day, and the teacher just got fed up with it and said, "Carl, go to the corner, and what I want you to do, I want you to add up every integer from 1 to 100. So we have 1 plus 2 plus 3 plus 4 plus 5. Now he thought that Carl was going to sit in there for most of the morning because it's a little kid adding up these things. He didn't have a calculator, so he had to do it by hand. Well, Carl just went to the corner, sat there for a little bit, and then went back to the teacher and said, "It's 5,050. And the teacher was just perplexed at what he just did, because he thought that Carl actually added them all up in his head. What Carl did instead is he recognized a pattern. He said, if I'm adding 1 through 100, well, if I add 1 plus 100, that equals 101. If I add 2 plus 99, that just equals 101. If I go 3 plus 98, that just equals 101. And he said to himself, well, they're all 101 pairs, and because I have 100 terms, I'm going to have 50 pairs. So he just said, well, I'll just take 101 and multiply by 50 to get 5,050, and that is the sum of all the integers from 1 through 100. Well, the awesome thing about what this guy discovered when he was a little kid, that just this little trick here actually works for any arithmetic sequence. All you need to do is come up with these pairs, and notice they're all the same, so you really only have to take your first and last term, and you're going to multiply it by half the number of terms you have because you created all of these pairs. And magically this works for any arithmetic sequence. And it seems like it doesn't work, and we'll see problems where it doesn't look like it should work, but it's going to work and give us our partial sum. So arithmetic partial sum. The symbol for that is that S sub n. That stands for partial sum of an arithmetic sequence. Remember, everything we're learning today just works with arithmetic. All right? So it has to have a constant difference. 1 through 100 is obviously arithmetic because you count up by 1 each time. You keep adding 1. All right, so depending on the information we can use either one of the following formulas. Don't use the second one. In fact, I'm going to have to look it up again to write it down. We're just going to use this first one. And the first one is just, hey, take our number of terms, divide it by 2. Then multiply it by our first term, added to our last term. So a sub n stands for our last term. And just because it is true, there is another formula, and that is n divided by 2 times 2 times our first term plus n minus 1 times our common difference. I am never going to use this with you. I'm never going to use the second one. I'm always going to use the first one. Because either one of them I need to know my n values. This one, that's all I just need the first term, last term, and my n value. This one we have to come up with all this. I got first term, I got my n's, I got to come up with my difference, and I got to do this crazy formula. Either one works, but we're going to stick with this first one. It's going to make your life a lot easier. Like I said, every time I do the second one, I have to look it up again because I just don't ever use it, so it doesn't stay in the old brain housing group. Okay, let's see this guy in action. So the first thing we have to do is confirm that it is arithmetic. So to do that, we're just going to check to make sure there's a common difference. So this is minus 3, and I promise you that pattern continues all the way through. So this is, in fact, arithmetic. All right, to use this, we need to know our first term. I need to know my last term. And I need to know my n value. Well, my n value is going to be 1, 2, 3, 4, 5, 6, 7. Which makes my last term, notice this n was just a placeholder till I got it. So a sub n actually equals a sub 7, which is, bless you, which is 22. And a sub 1 is 40. So to get my partial sum, my S sub 7, that's just going to equal my n's divided by 2, how many terms I have, and we just take our first term and add it to our last term. And that's going to come out to just 217. Do you trust me that works? If you don't, do it. I do this every single time because it just doesn't feel like it should work. It's just like, how does it... do you see a subtract 3 in here? Is there a minus 3 in here? So this formula somehow works out the fact that it knows the difference just by adding those first two terms, or the first and last term, and then just counting up your numbers. And this will work on any arithmetic sequence. Who did the adding? Did it work? It works. It works. It's crazy, but it works. All right, we're going to do the integers from 1 to 35. Are we convinced that's arithmetic? Yeah, I'm adding 1 every single time. So I need my first term. Well, that's easy. My first term is going to equal 1. Let's go ahead and find my n value. This is a tough one. I have all the numbers from 1 to 35. How many terms do I have? It's not a trick question. How many terms do I have? Just shout it out. Anybody? I have 35. Thank you. So that means my last term is a sub 35, which just happens to equal 35 as well. So now we just put in our s of 35 is going to equal 35 divided by 2 times our first term plus our last term, and that's going to equal 630. All right, our next guy. We now have it in series notation. All right, so we are going to do the same information. I want to find my first term. Well, my first term is going to be plugging that 1 in for that I. So my first term is just going to be 3 times 1 minus 5, which equals negative 2. How many terms are in this sequence? Matthew? I have 15. I have 15 terms. Can someone give me an instance where this number's 15, but I don't have 15 terms, John? If my index equals anything but 1, right? So if my index was 2, I would actually have 14 terms, because we'd have 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13, 14, 15. That's only 14. All right? So if this was 2, 3, 4, 5, 6, even if it was 0, negative 1. So don't always rely on this to tell you your terms. You might actually have to count it up. Okay? So going from here to 15, turns out there's 15 terms, so my n is 15. Which means my last term is going to be a sub 15, which is 3 times 15 minus 5, which equals 45 minus 5, which is 40. Which means my partial sum, s sub, we have 15 terms, equals 15 divided by 2 times my first term plus my last term. And that's going to go ahead and equal 285. These are the problems that make this seem even weirder, that I started with a negative number, added a positive, and I could still come up with our sum. Because in fact, this is the only negative number that's here. The next one would have been positive. So it's weird that those pairs actually work out like that. But they do. And we can trust it as long as we know it's arithmetic. And I didn't really prove this one, but it is arithmetic. The last one is arithmetic as well, because we're adding 5, adding 5, adding 5, adding 5, adding 5, adding 5, adding 5. Here is our problem. I know my first term. I know my last term. But my n, she's a mystery. She is a mystery. There's a few ways to find our n. Does anyone have a plan to find an n? John?
Do the last term minus the first term over the determinant.
Last term over the first term? Say it again.
Last term minus the first term over the determinant.
Oh, okay.
Because then you have like the difference between the two, and then every in group will be on 4, so you have a...
We're missing just a little bit of that, though. Because you're saying do 91. Say it again. 91
minus 36.
Minus 36
5.
over 5. What does that come out to? 11? It is not 11. It's close. It is not 11 because we're not accounting for that first term. It was a good thought. It's close. That will work if it's an even number of n's. Anyone have another way? Even if it's painfully long way. What could a painfully long way be? Matthew? Just keep adding 5 till you get 91 and count your terms. Callie, you got another way?
Well, I was going to say that one's not that hard because you can see that it's 36. So it'll be the 6 of that and then the 1 of the next and then the 6 of the one.
So it wouldn't be that hard to write it out and count either. What if it was like 2.7 or something? Then we probably don't want to do it, right? So if we're ever missing something, if I'm missing my first number, my last number, or n, it's probably a good idea to write your explicit formula down. And since we're going up by 5, my explicit formula would be a sub n equals my d, my difference, which is 5n, plus our c, and remember our c is our first term minus our difference. So our first term was 36 minus our difference is 31. So that is my a sub 1 minus the d. I just want to write that again because we haven't written it for a while and it's good to have in your notes. So this is the only small tweak that John needed to make to his formula is the fact that it's 31. He needed to subtract the difference from the first one first. That's why I was trying to lead you. I kept saying, should we subtract the d? And you're like, no, we just divide it. I'm like, okay, if that's what you want to do. All right, so we know the last term is 91. We are going to have 91 as my last term. Is going to equal 5n plus 31. Subtract 31. We have 60. 60 divided by 5. We have n equals 12. Not quite 11. Pretty close. But we didn't account for that difference to start off with. So realistically, what John figured out is John solved from 41 to 91 with his formula. Yeah?
Couldn't you use that, but then just add 1 at the end? Just like to get the right number of terms?
Yeah.
Would that be easier?
Define easier.
Well, it would take less work. Wouldn't it?
I don't know if it would take less work, because I can write this formula just as fast and do this all in my head, just like adding and dividing by the difference. It's your preference. And the problem with doing that is, are you always going to remember to add 1? You will?
Yeah.
Okay, well then you'll be fine. It's just, I know how to make this formula. I won't remember a year from now to add 1 every single time.
Good.
But this I can remember. But yeah, if you want to do it that method, go ahead. All right, so our n equals 12. So that means we're going to have our partial sum equals 12 divided by 2. And that'll just be our first term plus our last term. And our total partial sum is going to be 762. But JP, the reason why I would never teach it that way is because most people won't remember to add 1. They'll just go, oh yeah, I remember that. You just add your first and last and divide by 2 and you're done. All right, it's the nature of the beast that you forget a little 1 on there, which is a big difference in this problem. Okay. So we just have homework up. Oh no, I have a word problem. I forgot about the word problem. Ugh. I always forget about word problems. But that's cool, because this one is in the homework too, almost the exact same problem. So we have to find the total salary for an employee who's paid $20,000 his first year and gets a $1,200 raise every single year after that. Well, that just means our sequence is $20,000. And then the next year he gets paid, I should use that. Yeah, let's just not use commas. We'll be fine. All right, the next year he's going to get paid $21,000. Was it $1,200? Yeah. $200. The year after that, he's going to make 22,400, and so on and so forth. Okay, so this is an arithmetic sequence because everything is increasing by 1,200. So that means my first term is 20,000. My common difference is 1,200 because I'm adding 1,200 every single year. So that means my explicit formula is going to be my difference, which is 1,200 times n plus RC. And just remember, RC is our first term minus our difference. That's going to be 18,800. I'm going to put that in the notes where I got that number from once again. Just in case you're studying this, where did I get that number from? I got it from the fact that it's our first term minus our difference. So a sub 1 minus our difference. That's where I get that number from for the arithmetic sequence. Alright, it says that it wants us to find the mean after 40 years. So I need to find that 40th year. I need to know how much he's making on that 40th year. So all we're going to do is we're going to plug 40 in for that n. So a sub 40 is my 40th year, is going to equal 1,200 times 40 plus 18,800, which is just going to equal 66,800. All right, so on that 40th year, he's making 66,800. So we're supposed to find the mean of the 40 annual sales. Well, the mean is adding everything up and dividing how many we have. So I need to get that sum. I need to get how much he actually makes in 40 years. If he doesn't spend a cent of it, how much he just makes and banks over 40 years. To do that, we need to do our partial sum equation. So our partial sum equation for 40 years is going to equal, I have 40 years divided by 2, so I have 40 terms divided by 2. And we're going to multiply by his starting salary of 20,000 plus his end salary of 66,800. So in 40 years, he makes a grand total of $1,736,000. So if you're only getting paid $20,000 and you get a modest raise each year, after 40 years you're a millionaire. That's that can-do attitude. As long as you're not spending money on anything else, you're a millionaire. Is that the average though? Did he average 17 million or 1,736,000 each year? Yes. No, it is not. So we need to find our mean. And those of you in statistics, that X with a bar above it means our mean. And our mean is just going to equal that 1,736,000 divided by the number of years it took to make it. And that's going to equal a grand total of $43,000. Well, and $400. $43,400. All right. The rest is just homework. I do want to note, though, while pasting pictures and stuff, it's a fun problem, but that can one is not on the right one. I showed the picture of the cans, but the cans is actually the one previous.
Wow.
It's not going to kill you. It's just a picture. It doesn't actually help.